So, dear students, we have a pulley question here. Here, there is a man of mass capital M. He's standing inside a trolley, जिसका mass small m है, and the rope goes over a pulley, and he's pulling it down with a force F. Now, our job is to one find out what is the minimum force required to just hold it there. Second, what would be the acceleration in the upward direction if the applied force is greater than that minimum force, right? And the third is what is the normal reaction experienced by the floor of this trolley by the man. Now, how we do it is we have to first of all look at a free body diagram. But before we do a free body diagram, let us see what are the tension forces in the rope. If the rope is being pulled by a force F, which means that there will be a force F in the up direction and an equal force, same rope hai, will also be there in the up direction. If I consider this as a system and we draw a free body diagram of this system means capital M plus small m. So when we draw a free body diagram, we should write the mass of that system, capital M plus small m. What are the forces that are acting in the upward direction? F and F. F plus F, we'll mark it as 2F. So 2F is a force acting in the up direction, right? And what is the total weight, the gravitational force in the down direction will be capital M plus small m into G. And let us suppose this accelerates with an acceleration A in the up direction. So if I use the force effect law, which means that the net force is equal to mass times acceleration. And we can clearly see here that net force, up force is 2F minus down force, capital M plus small m into G will be equal to capital M plus small m times of acceleration. That is my equation number 1. Let me hold it there. Now, if we want to find out the minimum force required when acceleration A is 0, the trolley remains at rest, then that force will become equal to F minimum. So this will become 2 times of F minimum minus capital M plus small m into G will be equal to 0 because acceleration is 0. So from here we can find that the minimum force required to hold this minus goes on that side. We have capital M plus small m into G divided by 2. So that is the minimum force required. So minimum force is how much? The total mass of the system into gravity divided by 2. Now look at it logically. Why 2? Because there are 2 ropes that are holding it together. So pulleys give us an advantage that applying one force, this gets multiplied by 2. Less effort is required through a pulley in this case. Now, if I want to find out what is the acceleration of the system, then we look at this equation and we find that acceleration will be equal to 2F minus capital M plus small m into G whole divided by, I will take this mass down, M plus small m. So that is the acceleration when F is greater than F minimum. Right? Make sense? Good. Now let's look at the normal reaction offered by this floor. So normal reaction will act in this direction. Now our focus is on this man. So the force acting down is mg, normal reaction is n, and he is pulling it up with the force F. Right? And it produces some acceleration A. Now in this case, we find that there is a force F in the up case, downward force is mg, right? And then there is a normal reaction here in the upward direction. So what is the normal reaction when we are again talking about that? So we'll have capital N plus F should be equal to mg if he's holding it there. If he's holding it there. Now, if there is an acceleration, let's say when it is holding, so then the force will be F minimum. Then the normal reaction, N will be mg minus F minimum. In the previous slide, we have calculated the F minimum. We can put it here. The F minimum, we get, so this mass is capital M of the person. So capital M. So capital Mg minus capital M plus small m into G upon 2. All we have to take now is an LCM, and we solve this. We find that normal reaction comes out to be M minus small m upon, yeah. So we'll just solve it and you get your answer, right? Take an LCM, you get your answer. Okay, solve it up. Thank you very much.